Swayam Prabha. Digital India. Educated India.
Welcome back, students. So in the last lecture we started with the problem, and then I went back and showed you what different values of a, b and c are. So solve this problem, we will use the whiteboard. So the best way is always to solution to given. First we write what the things are given. Okay, so the equation is given 1 minus m square phi xx plus phi yy. So drawing the analogy from the general equation, we write a is equal to 1 minus m square. Second, b is 0 and c is 1. So the first part, we say when m is less than 1, we have to calculate the value of b square minus 4ac. So b is 0, so 0 minus 4, a is 1 minus m square into 1. So minus 4 plus 4m square, or 4m square minus 4. All right, we have been given m is less than 1, right? It implies m square will also be less than 1, right, which implies 4m square is less than 4, right? So if you bring 4 on this side, it will become 4m square minus 4 is less than 0. All right, therefore this value 4m square minus 4 or b square minus 4ac will be less than 0, which means it is an elliptical PDE. All right. So in the second part, when m is greater than 1, we have found out, doesn't matter what the value, but b square minus 4ac came out to be 4m square minus 4, right? So when m is greater than 1, this means 4m square minus 4 is going to be greater than 0, which implies b square minus 4ac is greater than 0. This implies it is hyperbolic PDE. Okay, now the third part is, I'll rub this one here. B square minus 4AC when m is equal to 1. So b square minus 4ac came out to be 4m square minus 4, right. So when m is equal to 1, 4m square minus 4 is equal to 0. This means it is parabolic partial differential equation. So this is how we have solved the problem. All right. So I'll just write the solution here. So when m is greater than 1, it was elliptical PDE. M greater than 1, it was hyperbolic. And for m is equal to 1, it was parabolic PDE. Okay. So time to move onwards. We will solve another problem. So it says that consider the function phi of xy as e to the power x plus e to the power y, and we have to consider the point x comma y as 1 comma 1. We have to calculate the exact values of del phi del x and del phi del y at this point, at point 1 comma 1. Secondly, use the first order finite difference with delta x is equal to delta y is equal to 0.1 to calculate the approximate values of delta phi by delta x and delta phi by delta y at 1 comma 1, and calculate the percentage difference with exact values. So this is the application of all the things that we had done in the last lecture. Okay, and this will be a good way to understand so solution number 3. So what we know that the function phi x comma y has been given as e to the power x plus e to the power y. So for the first part, we should be able to calculate del phi del x will be e to the power x, correct, and del phi del y is going to be e to the power y, simple partial differential. Okay, so we have to calculate del phi del x at 1 comma 1. It's going to be e to the power 1 or 2.7183. Similarly, del phi by del y at 1 comma 1 e to the power y, that is e to the power 1, 2.7183. So that was our first question, that we have solved the values of del phi del x at 1 comma 1, del phi del y at 1 comma 1. In the second part, we have been given that delta x is equal to delta y is equal to 0.1. This is what we have to assume. Let 1 comma 1 be denoted by I comma j. Okay, and if we use first order forward difference del phi del x at I comma j can be written as phi of I plus 1 comma j minus phi I comma j divided by delta x, okay, or del phi del x at I comma j can be written as phi of phi at what point? 1, because delta x is 0.1, so 1 plus delta x, so that is 1.1 comma 1 minus phi at 1 comma 1 divided by 0.1. This will be e to the power 1.1 plus e to the power 1 minus e to the power 1 plus e to the power 1. Alright, we are just putting in the values, and if you use your calculator, it's going to be 2.8588. Alright, that is del phi del x at 1 comma 1. So we are going to erase everything here and proceed. So similarly, del phi by del y I comma j will be phi of I comma j plus 1 minus phi of I comma j divided by delta y, or the value of the function at 1 comma 1.1 minus phi at 1 comma 1 divided by delta y 0.1, or e to the power 1 plus e to the power 1 plus 1 minus e to the power 1 plus e to the power 1 divided by 0.1. This is 2.8588. So percentage difference for both cases is 2.8588 minus 2.7183 divided by 2.7183, and this percentage difference come out to be, if you 5.2%. All right, so this is the answer. All right, so this was the simple most question and the solution for demonstrating the percentage difference and the concepts that we have learned in the last lecture. So we proceed from this point now to, we mentioned about other schemes of the meshing, that is the introduction to finite volume method. What is finite volume method? So the finite volume is the subdomain method with piecewise definition of field variable in the neighborhood of chosen control volume. All right, so the total solution domain in the finite volume is divided into smaller control volume. So the total solution total domain is divided into smaller control volumes. Normally they are rectangular in shape or quadrilateral in shape. So the nodal points are used with these control volumes for interpolating the field variable, and usually a single node at the center of the control volume is used for each control volume. So So this is the one single point in that control volume that is used, and this is based on the cell balance equation. It is solved by the integral approach, which is more accurate than the finite difference method because it is free from truncation errors. So one thing about the integral approach is that it is free from the truncation errors. Cell structure is shown in this figure here. You see, this is the control volume, the dashed zone, and this at the center point, we calculate the things. Simple is one method which is called semi-implicit method for pressure linked equations. So simple algorithm is based on finite volume vector. This is just one example of finite. So this was just something about the finite volume method. So now going to the things that are very much relevant to our hydraulic engineering course, that how do we model or do the numerical modeling of the turbulent flows, okay, because most of the flows in real nature are turbulent. So turbulence is a three-dimensional unsteady phenomena. So it is a function of time, and it's also a function of a space. So huge amount of information is needed for the proper description of the turbulent flows. That is a very well established fact. Hence, an ideal turbulence method must be able to capture the features of the turbulent flow field at a minimum complexity level. So ideally, the best of the numerical model that can do this type of turbulent flow modeling should be able to capture the features of the turbulent flow with least complexity level. So the model should be least complex as well. So turbulent flows can be modeled numerically to capture the temporal fluctuations, the time average features of the flow field. So the real velocity, the fluctuations mean the deviation from the average velocity, and the time average features of the flow field. So because these two affect the turbulence in terms of turbulent stresses, these two quantities. You remember we mentioned about U prime and U bar in our laminar and turbulent flows. So average flow properties and the turbulent fluctuations are actually coupled. And why are they coupled? Due to non-linear nature of the turbulence. This is all the information that we know from before. And for this particular reason, we cannot ignore the fluctuations under any circumstances. So an ideal turbulent model should be able to capture all these fluctuations too. This turbulent flow is comprised of vortices with a range of different sizes. Simulations of all scales of the vortices is not possible. The vortices could be very small as well. So the modeling of the smallest of these vortices might not be possible, because the reason is we have limitations on the available computational facilities. The time when the quantum computing is a reality, this might be an easier thing to do, but for now, until that point, we still consider that our computational facilities where we are able to capture all the scales of vortices is not yet possible. Further, a universal turbulence model which is valid for all the turbulent flows is not yet available as well. Okay. So with this background, we come to one of the most important techniques to solve these Navier-Stokes equation, and this is called Reynolds average Navier-Stokes equation. As the name indicates, what we do is we do the averaging of the Navier-Stokes equation. Reynolds, because Reynolds was the first scientist to do it. So we have already discussed this term called Reynolds decomposition. We have already discussed this in laminar and turbulent flow module and the Reynolds condition. Okay, if you are able to recall, just in a case where you are not, I have included that again as a quick repetition. So what is Reynolds decomposition? For the instantaneous velocities u, v, w and the pressure P, u can be written as u bar plus u prime, alright, and v is written as v bar plus v prime. This is the bar, whatever is under bar denotes the average value, and whatever is with the prime, it indicates the fluctuations. Okay. Similarly, W is written as W bar plus W prime, and pressure is written as P bar plus P prime. So if we say that F dash and D dash are any two general fluctuating parameters, we also have dealt this in our previous slide, then the average of F bar and G bar is going to be 0. So F prime whole bar and G prime whole bar is 0. Also we know that F prime multiplied by G prime and taken the average of that quantity is not equal to 0. If you recall, we had Reynolds shear stress is U prime W prime. If this was 0, then there would be no Reynolds shear stress, right? But this is not equal to 0, therefore is a finite shear stress. Alright. The third is the del F prime. So the del S of the fluctuation, the first differential and also the second differential, and if we take the whole bar is equal to 0. Also if we multiply both the fluctuations F dash D dash and take the differential and average it, it will not be equal to 0. Alright. So these are called the Reynolds condition. So this we have already seen before. So for a velocity field ui, we can write ui prime into uj bar to the whole bar is equal to 0. Also ui double bar is equal to ui bar. If you take the average of the average, it is the average itself, and the fluctuation, if it is averaged, it is 0. Alright. This is Reynolds averaging. So the continuity equation for the incompressible flow is this: del uk by del xk is equal to 0, right? And if we perform the Reynolds averaging on the above equation, it's going to yield one equation, that is del uk bar by del xk bar is equal to 0, right? You don't have just uk, you can write uk bar plus uk prime. Alright, and so del uk by del xk will be del uk bar by del xk plus del xk uk bar, and this will go to 0. Alright, so this can be represented as this. The Navier-Stokes equation for an incompressible flow can be written as del ui del t plus del ui uj by del xj is equal to minus 1 by rho del p del xi plus del xxj 2 nu dij. This is the standard form of All right. So Dij here is a strain rate tensor, which we have seen in the last lecture in our viscous fluid flow, where Dij is written as half of del ui by del xj plus del uj by del xi. I think this is not a problem because we have derived it. So if we do the averaging of Navier-Stokes equation, if we put u is equal to u bar plus u prime and take the whole average of the equation, so sorry, u is equal to u bar plus u prime and v is equal to v bar plus v prime and w is equal to w bar plus w prime and p is equal to p bar plus p prime, and put it into Reynolds average equation and do the whole average of the equation, we are going to get equation like del ui by del t whole bar, del ui bar, del uj bar. So if you see, this is average term, this is average term, this is average term, this is also average term, and this is also average term, right? So if we use equation 2, the above equation, you see, you remember that equation 2, this one here, del uk bar by del xk is equal to 0, using the continuity equation, it can be written as del ui bar by del t is equal to minus 1 by rho del p bar by del xi plus del xj of minus tau ij plus 2 nu dij. All right. Okay, this is equation number 5. So this actually is nothing but Reynolds average Navier-Stokes equation. There is some things that we need to find out. What is tau ij? Dij we already know. So in the above equation, tau ij is ui prime multiplied by uj prime. This is generally called Reynolds shear stress, and as we have read about it, it is much more than the kinematic stress. And tau ij here is a symmetric tensor. Symmetric means ui prime uj prime is equal to uj prime ui prime. So the term rho into, when rho is multiplied by tau ij, is known as turbulent stress or Reynolds stress. All right. The objective is to solve the Reynolds average continuity and momentum equation to obtain the average flow field ui bar and rho. Okay, so the objective of this thing is to solve the flow for ui bar and p bar. We want to find out the average quantities. That is why we do some turbulence modeling. Okay. So how do we do it? We solve the Reynolds stress equation. If we subtract equation 2, the beginning equation, second equation from equation 1, we can get del uk prime divided by del xk is equal to 0. Similarly, if we subtract equation 4 from equation 3, you see equation number 4, this one is 4 and this one is 3. All right. So what we are doing is we are subtracting the average to a general equation in both the cases. We are going to get del ui prime del t plus uj prime original equation minus averaged equation. All right. Same is here, original equation minus averaged equation. And why do we do this? To obtain fluctuation equations. So with that, this is how we obtain the equations with fluctuation terms in terms of differential equations. All right. If expressing uj bar into del ui bar, uj prime into del ui prime del t plus ui in terms of equation 7. Okay. So if we express that in terms of equation 7 here, and this is called the Reynolds stress equation, where this Pij is called the production of Reynolds stress, this pi ij is the pressure strain correlation tensor, and epsilon ij is the dissipation, where jk is diffusive flux. You can try to do this at your home, but the derivation of this is outside the scope of the current course. I have shown you the methods how to get one equation from the other, but the details is not in your course curriculum. All right, and this is Reynolds stress equation, equation number. Pij is given as minus tau ik del uj by del xk minus tau jk del ui del xk. This is the expression of the dissipation, production and pressure strain correlation factor. Epsilon ij is the dissipation. It is expressed like this: 2 nu del ui prime del xk del uj prime del xk whole bar. All right, where jik is given in this form. This is velocity fluctuation, this is pressure fluctuation, and this is fluctuation due to the viscosity. Therefore, jtijk can also be written as ui prime, uj prime, and uk prime. Or you see, this velocity fluctuations is written like this, the pressure fluctuation is written like this, and viscosity fluctuations is written like this. So we have seen what all these terms of what all these term means for this Reynolds stress equation. You see this one here: Pij, pi ij, production of Reynolds stress, dissipation, diffusive flux, and pressure strain correlation factor. So you don't need to remember all the details here, but the way of doing it is quite an important, and somebody who would be interested in doing further research or further studies in M.Tech, this will be a complete course in itself. Okay, so now how to close this problem is the important question, and that will be the topic of our next lecture, and we will also proceed with techniques like direct numerical simulation and large eddy simulation for the modeling of computational fluid dynamics. So this will be all for today. Thank you so much for listening, and I'll see you in the next lecture.